This is part 2 of our series on pump calculations. So this covers section B1, chapter 13. And in the previous section, we looked at density calculations and looking at pressure at depth, which we did earlier in the semester in our fluids dynamics portion. This portion, we start talking about pumps and some of the terms we use to describe their performance and the way that we have systems set up using pumps. Okay, so we've used the term head before, and when we talk about pumps, we often use head instead of other measurements. And head in this case is a measurement in meters. We talk about the head of the fluid as a way to either talk about the pressure or maybe the energy inside of that fluid. We saw an equivalent head, right? So we saw when we did some of our labs, we saw we had columns of water and those represented different levels of energy inside of the fluids. And we could visually represent losses of energy as those columns tended to change in height. We also have introduced Bernoulli's equation, right? And Bernoulli's equation had a whole bunch of terms, but we had arranged them all so that all of the units of Bernoulli's worked out to be meters. So what we had were 3 different types of head measurements all combined into each side of Bernoulli's equation. Okay, so the first term that we're going to introduce that involves head, or that amount of energy in the form of height, is the static discharge head from the pump. Now, the static discharge head, first of all, discharge means it's on the outlet of the pump. So it's leaving the pump. And the idea of static would be that this is the amount of energy just to keep the system still. Okay, so if we're talking about this sort of the pump energy or the energy in our system, we have to consider how much is on the outlet side and how much is it just to keep the system still. Okay, we'll see kind of what that means in a moment. So the definition for the static discharge head is the vertical distance from the center line of the pump to the surface of the liquid being pumped into an open tank. That's the static discharge head. So let's just draw a little diagram so we kind of understand what that means. Okay, so here's a diagram to describe this. We have a pump, and our pump is able to discharge fluid, and that fluid is going to make its way up to, let's say, some tank that has some water in it. So we have our pump, and we've got some center line from the pump, height-wise, so wherever the center of that pump is, compared to the height of the fluid, and the distance that we would consider here, the vertical distance we would consider to be our static discharge head. Now, there's 2 special cases when it comes to a static discharge head. Okay? It involves where does the final fluid sort of end up leaving the system. Okay, so case number 1, if the pipe enters the open tank and it's above the level of the water. So we have water that's entering into the tank above the water level. And when we have this, we have to consider where does the fluid leave the pipe. And we could have 2 different situations. First one, so it just drains in and it kind of leaves horizontally. And in this case, yes, we would consider our top height of our system to be the height where the water left that pipe. We also could have a case where we have sort of like a downward spout, okay, so a siphon type arrangement, and we wouldn't take the very highest point of this system. Because of the siphon action, we would take the point where the fluid leaves that pipe. Okay, so whatever the outlet of the pipe, as long as it's above the water level. Case number 2 is if we have the pipe entering the water itself. So the outlet of the pipe is below the surface of the water. And in that case, well, we're just going to take the surface of the water as our upper height when we measure our static discharge head. Let's look at the suction side of our system. So we have a static suction head, just like we had a static discharge head. And the suction head is on the suction side, or the inlet side of the pump. So when the suction side open tank is above the pump, the height from the pump center line to the fluid surface is called the static suction head. So here's what that means. We have a tank, and it's got some fluid in it. And then we have a discharge from that tank, and it makes its way to the pump, which then would continue on through my system. And so in this case, once again, we go from our center line of our tank to our level of our fluid, and we would consider this to be our static suction head. Okay. Looks very similar to our static discharge head, same sort of diagram. Now we don't have those two cases because if the pipe was above the water level, it wouldn't be able to suck any fluid. So that one's always underneath the water level, so there's no confusion as to where our measurements would take place. We have another situation on the suction side, which is known as a static lift head. Okay, and this would be the case where we have that tank, and instead of being above the pump, it's below the pump. So the height measurement is sort of a below the pump, or almost like a negative measurement, so a downwards measurement. And what that would look like would be if we had a tank and we had an outlet from our tank that then moved up to our pump. So we got our pump here, and then it would continue on to the rest of the system. So in this case, our static lift head would be from the center line of the pump down to the water level. And so that would be our measurement of our static lift head, would be that height measurement. If we look at our system where we've combined our suction head and our discharge head, then we can look at the total change of heights and come up with a total static head. And so because we have two cases where we have either a suction lift head or a static lift head, or we have a static suction head, we have two different ways that we can kind of visualize our total static head. So let's look at it when we have suction in the first case. So with our suction side, what we would have would be a tank, and we would draw water from it. It would go through a pump, and then our pump would take us up to a higher level. And again, in this case, we are entering that tank below the water surface, so we would use the water surface as our measurement. If we were dumping above, then we would take the outlet of the pipe as our measurement. Okay, and so in this case, what we would have would be a few different ways that we can measure this system. So what we had was a distance here. So we had a distance here, which was our static suction head. So the distance from the water line on the supply side of that pump down to the center line of the pump. Okay. We also had a measurement from the center line of the pump up to the water level here. Okay, and that was our static discharge head. Okay. And if we considered the difference between those two, okay, so the height difference between that water level and this water level, what we get would be our total static head. Okay, so we have the difference between the two. When we consider those two, how much we have left over in between the two, it provides us with the total static head. So really the difference in head that that pump has to provide in order for that system to just be stable. Okay, so in this case, what we would say is that our total static head is equal to my static discharge head minus my static suction head. Okay, so my total static head here is equal to my largest value, my discharge head, minus my suction head. Okay, let's look at the second case if we have static suction lift that's occurring. Okay, so let's draw out our system. What we would have would be a low reservoir. It would move upwards to my pump, and then from my pump I would move up to a upper reservoir. Okay, so in this case, I would have one measurement which was from my center line of my pump, right here from the water level to the center line of the pump, and that was my static suction lift. The measurement from my upper reservoir height down to my center line of my pump was my static discharge height. And the total height, so my total static head, would be the difference between the two water levels, and that would be my total static head. Okay, so in this situation, if we talk about what my total static head is, it's going to be equal to my static discharge head plus my static suction lift. Okay. So in the previous one, I had a negative, I subtracted a value. This one, I've added. So the equations are a little bit different. And in this case, it really does make sense to work off of a diagram. It's sometimes very helpful to use sort of the diagram to visualize a difference between those two arrangements. To circle back to Bernoulli's, just to kind of explain really what we're doing from Bernoulli's perspective. I've put down Bernoulli's, but in this case, I've added some more to it. So up until this point, we had the typical Bernoulli's equation, the V1 squared term, the Z term, the P term, and then we also had the head losses, which we talked about previously with friction in pipes and other losses, and then all of that equals the terms on the right hand side of the equation. However, what I've added into this now is the energy created by the pump. So the head from the pump. So we can add in all these terms into Bernoulli's if we have changes to the system, energy in or energy out. And so the head of the pump has been added now to Bernoulli's now that we've started this section. So why don't we talk about this in terms of what Bernoulli's looks like when we have open tanks and we have a pump that's connecting them. Okay, so first thing that we did when we talked about Bernoulli's is we assigned some points. So I would take my tank and I would assume I got point number 1, and my upper tank I might consider to be point number 2. And in between them, I've added some head from the pump. So the pump is adding some energy. In this case, what we're going to do is make some assumptions. Here's some of my assumptions. So assumption number 1, I'm going to assume no losses. Okay. Assumption number 2, I'm going to assume that the velocity at the top of the tanks, so at 1 and at 2, both of those velocities are going to be slow. We're going to assume they're 0. Okay, they're not going to be 0, but we're going to assume those tanks are large enough that it's not a noticeable velocity at the tops and bottoms of the tanks. And we're going to assume that both of those tanks, 1 and 2, are at atmospheric pressure. So number 1 and number 2 have no pressure to them. So that allows us to simplify Bernoulli's quite a bit. So we have velocities are 0, my pressures are 0, and really all I'm left with is going to be a few terms left over. So let's take a look at what that looks like. So some of the terms that are going to disappear, my velocities are 0, so velocities are going to disappear. My pressure is atmospheric, so those are 0 and they disappear. Losses, I've assumed at this point I don't have any losses. And so this is starting to look a lot better. I almost had a complete screen full of terms, and what I'm going to be left with is 3 of them. And so what it's going to say is that Z1 plus my head from the pump is going to be equal to Z2. And if I rearrange that, my head from the pump is going to be equal to Z2 minus Z1. So if I come back to my diagram, just like I did before, maybe I assign some heights based off of my center line of my pump. Okay, so in this case, I would have some Z1 value, and over here I would have some Z2 value. And if we relate these to what we just did, Z2 would be equivalent to my static discharge head, right? So that would be like my static discharge head. My Z1 would be my static suction head. And my head from my pump would be my total suction head. All right, so on equation form, that's what we just came up with. Your textbook gets a little twisted a little bit with some of those things, but if we go back to Bernoulli's, we can make sense of some of these terms and maybe where they come from. And if we get into the situation where we have a suction head or a suction lift, really with the idea that as we go up, it's a positive, or we go down, if it's below the pump, it's a negative, then Bernoulli's should be able to give us the right equation, whether it's a positive Z value or a negative Z value relative to that pump's location. Okay, so Bernoulli's can be a good tool if we start to use it for this type of thing in this kind of analysis. So as I was saying, your textbook outlines, okay, make sure you memorize this. If you have a pump with suction lift, then total static head is going to be the static discharge plus the static suction lift. But if you have a pump with a suction head, then of course it's going to be one minus the other. And, if you can draw the diagram and you can relate that, then that's one way you can remember this stuff. If you kind of roll back to Bernoulli's, that can also be a way that you could remember this stuff. But unfortunately, I don't have any other easier way to do it, to remember. Either we got to remember kind of this, we got to either draw a diagram and figure it out, or else rely on Bernoulli's for us to figure these terms out. Okay, so it doesn't really matter if we're looking at it visually, because either way, the total static head is going to be the difference between the inlet and the outlet heights of the system. So the heights of those tanks, or the height where we have fluid leaving the pipe on the outlet. Okay, so let's do an example. So we have pump that's transferring oil from a sump with an oil level 1.5 meters below the floor and into the top of an empty disposal tank at a height of 4.6 meters. So if the oil has a specific gravity of 0.89, calculate the static suction lift, the static discharge head, the total static head, and the total head pressure. Okay, so I think the best thing we can do in this case is to create a diagram. So here's what our system looks like. We have our sump, okay, so that's our lowest point here. And 1.5 meters up from the surface of the sump, we have our pump. Okay, we got our pump. And then the discharge from the upper pipe is 4.6 meters above, and then that drains into that upper reservoir. Okay, so we're going to try and figure out a few terms here. So let's figure out what is our static suction lift. Okay, so our static suction lift is the distance between the lowest level in our system, I guess the top level of that sump, and the center line of the pump. Okay, and so in this case, 1.5 meters is going to be our static suction lift. So 1.5 meters. We have the static discharge head, and that's the distance between the center line of the pump and two different cases. So case number one would be if we have a discharge from our pipe that is above the level of the reservoir, and that's the case that we have here. So we would take from that level, and we have our static discharge head here, and in this case we would have 4.6 meters. The total static head in our system, well, in this case it's a lift situation. So if we go back to that equation, it says you're going to add your discharge and you're going to add your static lift. But we can also look at it from the diagram perspective. So we look at the lowest level in our system on the suction side. And then we look at either the outlet from the top pipe or the water level, whichever one is higher. In this case, the outlet from the top pipe. And so in this case, our total static head is going to be that height. And in this case, 1.5 meters plus 4.6 meters. So 1.5 plus 4.6 is equal to 6.1 meters would be our answer there. We have one other thing we could find, I guess, if we were interested. How much head pressure do we have? So the total static head is one measurement, but if we wanted to measure it instead of in head in meters, how much pressure is it worth? So we know that pressure is equal to rho times G times H. And in this case, because our oil has a specific gravity of 0.89, so the rho of our oil is going to be equal to 0.89 times 1,000 kilograms per cubic meter. And that would be 890 kilograms per cubic meter. It's my rho of my oil. So my pressure is going to be equal to 890 kilograms per cubic meter times gravity, 9.81 meters per second squared, times my total static head, 6.1 meters. And in this case, my pressure ends up as 890 times 9.81 times 6.1, and I get 53.258 pascals, or 53.3 kPa. Okay, so that gives you some background on some static head calculations, which we typically see with open tanks. In the next module, what we'll look at is if we have pressure in our system, so pressurized tanks, and how does that impact our calculations. For the time being, you've finished off your second portion of this chapter, and you'll have a couple of practice problems that you can access on Blackboard to test out your knowledge on these terms.